weather changes, of course. Weather's always changing, but springtime, there are things that are happening that don't normally happen during the regular year. Here in the northern plains, we get a lot of melting, and as a result, there's a lot more water vapor in the atmosphere. So you tend to see a lot more IFR conditions in the northern plains. Across the United States, weather conditions vary. This time of year, this year, there's an El Nino. And as a result, you're seeing a lot more storms moving through California and also the southern plains of the United States. The East Coast, though, is right now kind of in a weather pattern where they're starting to see kind of changing conditions also. When I think about the spring, looking at spring weather, computer models. Forecasters use computer models as guidance to more or less forecast the weather, figure out what's going on. And as we transition from the winter into the spring, and then even into the summer, the computer models change. It's kind of like when you change oil in your car or your airplane, years ago we used to use single grade. Now you have multi-grade oil. But you would use one type of oil in the winter and another type of oil in the summer. The same thing with computer models. They use a set of equations for the winter and a set of equations for the summer. Now, in between, when do you change from one to the other? So that's a problem. A lot of the computer models don't handle spring weather real well. The height of the freezing level varies across the United States. During the winter, of course, the northern plains are completely below freezing. Southern plains tend to have a little bit higher freezing level. And it starts to change during the spring, so that in the northern plains of the United States, we start to see the freezing level going up. As a result, you tend to see a greater amount of icing across the northern plains. We talked about how water vapor evaporates, all the snow evaporates, or melts, I should say. The snow melts and then the water evaporates into the atmosphere. So the atmosphere is a lot more juicier. You have warmer temperatures, you have lots more water vapor in the atmosphere. That turns into clouds. And the clouds tend to be a lot more juicier. And as a result, you tend to see a lot more icing during the spring. Another thing to be concerned about during the springtime is warm fronts. Warm fronts, as we get these weather systems moving across the United States, they're tapping the counterclockwise circulation around a low, taps the moisture from the Gulf of Mexico. So you're starting to see moisture coming up from the Gulf of Mexico. That overruns the colder air up to the north and can produce freezing rain and also large areas of icing. That's another place where you find icing. Springtime also means thunderstorms. More in the southern plains, you tend to see thunderstorms. Especially with this El Nino cycle, you're seeing more thunderstorms, more severe weather. So the instability is there. You get this moisture coming up from the Gulf of Mexico. And as a result, they've been seeing more thunderstorms that are really vigorous. Thunderstorms that are topping out at 45,000 feet early this time of year, producing a lot of severe weather. You're getting large hail, tornadoes, and strong winds from these storms also. And reviewed the new aviation weather and the new aviation weather services.
Yeah.
Okay, these are new books that are coming out in probably by the end of the year, the end of 2016. And there's some big changes. And one of the changes in the aviation weather services is they talk about atmospheric soundings, the temperature profile of the atmosphere. Twice a day they send up weather balloons across the United States, all across the United States, to get a temperature profile. And they use those initial conditions to initialize the computer models, to set the models running for a forecast into the future. So pilots need to become aware of how to use SCUTs in their flight planning. And what SCUTs are, it's a plot of the atmospheric temperature profile, temperature and moisture profile, actually. And SCUTs tell you exactly where the freezing level is. And there are SCUTs that are observed, in other words, atmospheric soundings that are observed, and also atmospheric soundings that are forecast. So if you're lucky to live in a location where they're sending up a weather balloon, a sounding, in the northern plains here we have them in Chanhassen, we have it in Bismarck, Aberdeen, international falls, then you know exactly where the freezing level is right over your location. However, the computer models are able to forecast out into the future for any place across the United States. So if you live in Fargo, North Dakota, even though they don't send up a weather balloon, the computer model will forecast an atmospheric sounding, and you can actually look at that. So that's something that pilots who are pre-flight planning, it's good to do. So when you're flying ice, it's really important that you sit down and get a really thorough briefing. You need to look at all the available resources. And atmospheric soundings, temperature profiles of the atmosphere is one thing. Other things that you look at out at the Aviation Weather Center, they've got a great product that actually looks at icing in the future, what meteorologists call a nowcast, out to perhaps 6 hours into the future. But that's an integrated product. The icing forecast product, the forecast icing product, actually they call it, is an integrated product that takes in computer model information, also takes in satellite information, as well as radar information, and synthesizes that into a probability of icing. And then they give you that probability as an intensity for a given area, whether it be trace, light, moderate, or severe icing. So icing, of course, you need to know the freezing level. That's extremely important. And also you need to know cloud base, you need to know cloud top. Cloud top has been difficult to get. Pilot reports are invaluable, but there is also a new forecast product. Of course, pilots have been using the area forecast for years to figure out cloud tops, forecast cloud tops. That's going away by the end of the year. 2016, we will not see an area forecast, a textual product. Instead, the area forecast will be replaced with something called the graphical forecast, area forecast, or pilots are calling it now the GFA. And the GFA is using computer models to plot across the United States the cloud bases and cloud tops. So the computer model that it uses is the rapid refresh model. And what the RAP does is it, of course, forecasts out 18 hours into the future. And it can forecast cloud bases and cloud tops every hour. So when you go out to the GFA, you'll see it updated every hour. With the old area forecast, we had to wait every 6 hours to see a new forecast. This will be hourly. It's updated hourly. And the model uses a grid across the United States. And I believe the grid is a 6-kilometer grid, or no, 8 kilometer. I take that back. It's an 8-kilometer grid. So every 8 kilometers across the United States, there's a forecast for cloud base and cloud top. So a lot of pilots not aware of the changes that are occurring, and that's something that they need to educate. Pilots need education on. So. Well, with XM weather or with ADS-B weather, it's a NEXRAD imagery, and NEXRAD is the National Weather Service has a network of radars all across the United States, and they're overlapping, so you get, for the most part, seamless coverage from coast to coast. That radar, it takes a while for that radar to update, and it scans full volume. As it's scanning, around, going around and around, it's also tilting up, so you get a complete service volume. We call more or less a service volume. We think in terms of VORs as service volumes, but it does a radar volume. And after it does that, that's when it transmits its information, through a data link to the National Weather Service and also the network. Our network, where we're able to see it. So there is some latency issues. In other words, it takes 6 minutes before you get a weather image, a fresh weather image of what's happening. Now, also there's latency in the respect that it takes time to process that information and then also transmit that information. So a lot of times when you're flying and using ADS-B, the radar imagery that you see may be anywhere, well, at the very least it's 6 minutes old, but at the very most, not most, but it could be as much as 20 to 30 minutes old. And a lot of weather changes very quickly, especially convective. I mean, you look at the typical life cycle of a thunderstorm cell, a cell. And they're about 30 minutes in length, except for real severe storms that keep propagating. So, as a result, you may not be able to see the storms on your ADS-B that are now developing right in front of you. So that's a problem. That's why airborne weather radar is so invaluable. Airborne weather radar is continuously scanning. You're getting an image, every time it scans, and most radars typically scan, very quickly. You're getting an image probably once, or actually 2 or 3 images every second or so. So, airborne weather radar should be used more tactically flying around storms. Whereas ADS-B, the next rad imagery that you get from that, and also XM, they use the same thing, should be used for more strategic purposes. In other words, you're flying, you see out ahead of you a line of storms. Don't use ADS-B to penetrate or fly around those cells. You should use it to make a go, no-go decision, or to divert. Whereas with airborne weather radar, you could fly a little bit more tactically, looking at the cells, watching them develop, and then make decisions based upon the trends that you've seen.